Today we will study continuity and completeness. Let xt be a complete metric space and y be a subset of x. Then yd is complete metric space if and only if y is closed. It is given to us that xt is a complete metric space and y is a subset of x. Now first of all we suppose that y is closed. So in this case we need to prove that y is a complete metric space. We know that the space is complete if any Cauchy sequence in the space converges to a point in space. It means to prove that y is complete, suppose yn be a Cauchy sequence in the metric space yd. Since y is a subset of x, therefore yn is also Cauchy in a metric space xt. Since xt is a complete metric space, every Cauchy sequence in xt converges with x. It means Cauchy sequence yn converges to some point y in x. But yn is given to us that yn is closed. It means if the set is closed, it contains all its limit point. It means this point y belongs to y. This implies that Cauchy sequence yn, which is in metric space yd, is a convergent in y because it converges to a point in y. It means yd is complete. Now for the converse part, we assume that a metric space yd is complete. Now in this case we will show that y is closed. Let yn be a Cauchy sequence in a metric space yd. Because yd is complete, it means every Cauchy sequence in y converges to a limit y belonging to y. Because y belongs to y and y is any arbitrary point, it means y contains all its limit point. It means by the definition of closeness, y is closed. So we have proved that yd is complete if and only if y is closed. If it is given to us that xt is a complete metric space and y is a subset of x. Now we will state and prove Cantor's intersection theorem. Cantor's intersection theorem states that let xt be a complete metric space. Let a non-empty closed subset Fn be given for all n belonging to n such that Fn plus 1 is contained in Fn. Assume further that diameter of Fn tends to 0. In this case, intersection of Fn as n varies from 1 to infinity consists exactly one point. So we are given a complete metric space xt and we choose a point xn belonging to Fn for each n belonging to n, means n is a natural number. Because diameter Fn tends to 0, it means there is an epsilon greater than 0 and a natural number n such that diameter of Fn is less than epsilon. Therefore, for nm greater than or equal to n, with n greater than or equal to n and m greater than or equal to n, xm belongs to fm if fm is a subset of fn. So that distance of xm, distance between xm and xn is less than diameter of fn. Because diameter is defined as supremum of the points which belong to the set, and this is less than epsilon. It means we have proved that distance between xm and xn is less than epsilon. It means xn is a Cauchy sequence. Since x is complete, the sequence xn, which is Cauchy, converges to some point x belonging to x. Now we claim that this point x belongs to intersection of Fn where n varies from 1 to infinity. Suppose we fix this n belonging to n, means we fix this natural number n. Then the sequence fk, xk for all k greater than or equal to n is a sequence in fn and is a subsequence of this Cauchy sequence xn. So it converges to x, because this sequence is a Cauchy sequence and it is a convergent sequence, and this sequence converges to x. Therefore the sequence xk also converges to x. Because fn is closed, so it contains all its limit point. It means x belongs to fn for all n belonging to n. Because we have chosen arbitrary n, it means x belongs to all fn's, means fx belongs to intersection of fn for n equal to 1 to infinity. Now we wanted to prove that this consists of exactly one point. We have proved that it consists of point x, because we have proved x belongs to fn. Now we will show that it consists of exactly one point, means this intersection fn n equal to 1 to infinity is a singleton set. Suppose it is not a singleton set, means it consists of at least 2 points x and y belonging to this intersection and epsilon is greater than 0. It means there is a natural number n such that diameter of fn is less than epsilon. If x and y belongs to fn, then distance between x and y is less than or equal to diameter of fn, because diameter is defined as supremum of the points of the set, supremum of distances between the points of a set. So it means this is less than epsilon. So it means distance between x and y is less than epsilon, and this is true for any epsilon greater than 0. It means, because this cannot be negative, it means distance between x and y is 0, and this is possible only if x equal to y by the definition of a metric. So we have proved that there cannot be more than one point in this intersection, means this intersection consists of exactly one point. Now we will prove that a uniformly continuous function maps Cauchy sequence to Cauchy sequence. Suppose we have two spaces xd and y row. This is a set x equipped with metric d, and this is a set y equipped with metric rho. So let f is a mapping from one metric space to another, and suppose it is uniformly continuous function. So for given epsilon greater than 0, there is a delta greater than 0 such that for all xy belonging to x, distance between x and y, which is less than delta, implies that distance between fx and fy is less than epsilon. Here we have used d because x and y belongs to x, and here we have used rho because fx is the image of x under f and fy is the image of y under f, and these belongs to y. Here the metric is rho. So here the distance is measured with respect to d. Here the distances are measured with respect to metric rho. So distance of xy less than delta implies distance of fx and fy is less than epsilon. This is by the definition of uniformly continuous function. It means let xn be a Cauchy sequence in x. Now we have to prove that uniformly continuous function maps a Cauchy sequence to a Cauchy sequence. So we have considered xn to a Cauchy sequence in x. Now we will show that f of xn, which is the image of xn under f, is a Cauchy sequence in y. Because xn is a Cauchy sequence in x, it means there is a natural number n such that distance between xm and xn is less than delta for any mn greater than or equal to n. It means distance between fxm and fxn is less than epsilon for any mn greater than or equal to n. Here n is a natural number. This is by the definition of uniform continuity. Here in place of x we have xm, in place of y we have xn, in place of fx we have fxm, in place of fy we have fxn. Here it was xy, here it is xm, xn. So it means, what does it implies? fxn is a Cauchy sequence in y. So it means uniformly continuous function maps a Cauchy sequence xn in x to a Cauchy sequence fxn in y. If this is true only if the function is uniformly continuous. If the function is not uniformly continuous, then this theorem may not be true. For example, if fx is equal to 1 upon x is continuous on open interval 0 to infinity, and xn is equal to 1 upon n is a Cauchy sequence in 0 to infinity, but fxn is equal to the image of x 1 upon x under this 1 upon x means n is not a Cauchy sequence. So if the function is not uniformly continuous, then this theorem is not true. In this case, this is continuous on 0 to infinity, and this is a Cauchy sequence, but its image is not a Cauchy sequence because this function is continuous but not uniformly continuous, as we have studied in previous lectures. Let's see, now we will prove that CAB is complete. CAB means the set of all real valued continuous functions defined on the interval I equal to AB. Here the metric is defined as supremum of modulus of fx minus gx, where x belongs to the interval AB, where I is equal to AB, and fg are real valued continuous function. Now we have to prove that this set of real valued continuous functions, which we have denoted by CAB, equipped with this metric D, is a complete space. Suppose fxn is a Cauchy sequence in the metric space, which we have written as CAB. This is a set equipped with metric D, which is defined like this. Because this is a Cauchy sequence, therefore for given epsilon greater than 0, there exists a natural number n naught depending on epsilon, such that for all mn greater than or equal to n naught, distance between fxm and fn, fm and fm is less than epsilon. But how we define a metric in metric for the set of real valued continuous function? It is defined as supremum of modulus of fx minus gx. So it means supremum of fmx minus fnx is less than epsilon for all mn greater than or equal to n naught. Here f and g are continuous real valued functions and x belongs to the closed interval AB. And if supremum is less than epsilon, it means fmx minus fnx is less than epsilon. If we fix n and let m tends to infinity, we have fnx modulus of fnx minus fx less than epsilon, because Cauchy sequence is always convergent. So it means supremum of, if we take the supremum on both sides, supremum of fnx minus fx is less than epsilon. If you use this definition of this metric, then it means distance between fn and f is less than epsilon, because distance between f and g is supremum of modulus of fx minus gx. So supremum of fnx minus fx is distance between fn and f. And what does it imply? It means the sequence fn converges to f in x as n tends to infinity. It means the Cauchy sequence fn converges to f in metric space xd. What is x here? CAB. X here is CAB means set of all real valued continuous function. It means this metric space CAB equipped with metric D is complete. Earlier also in previous lecture we had studied some example related to interior, exterior and frontier. Today also we will study one example for open interval 0, 1 with respect to usual metric for R. If A is equal to open interval 0, 1, the interior of a set A consists of all points within A that do not touch the boundary. Since A does not include 0 and 1, it means interior of A is the set open interval 0 to 1. And we know that exterior of a set A consists of all the points outside A. Because A is an open interval, it does not contain 0 and 1. It means it consists of all the points outside the closed interval 0 to 1. Therefore, exterior of A is minus infinity to 0 and union 1 to infinity. And its frontier consists of all the points that are either in the set A or its complement, but not entirely contained in either. It means frontier of A is the set consisting of 0 and 1. Here I want to mention that a set is open if and only if every point is an interior point, and closed if every accumulation point belongs to the set. Secondly, interior of A is the largest open set contained in A. Closure of A is the smallest closed set that contains A. Boundary of A is their set theoretic difference, means complement of A naught means A bar minus A. This denote closure of A, this denote interior of A. One more example. To find closure, interior and boundary of the 1 point subsets 1 and 0 in the set of real numbers equipped with standard metric. Earlier we have calculated for open interval 0 to 1 and closed interval 0 to 1 in previous lecture. The closure of 1 when it is a singleton set is 1, because 1 does not have any limit point other than 1 itself. Also closure of 0 is 0, because 0 does not have any limit point other than 0 itself. For the interior, the set of A is the largest open set contained within A. For 1 point subsets, the interior would be interior of 1 is 5, means the empty set, because a 1 point set does not contain any open interval. Interior of 0 is also empty set, because 1 point set does not contain any open interval. Then how to calculate its boundary? The boundary of a set A is a set of all the points that are both in the closure of A and in the closure of the complement of A. So for 1 point subsets, the boundary of 1 will be empty set, because 1 is closed set and does not contain any limit point other than 1 itself. Also boundary of 0 is empty set for the same reason, because 0 is a closed set and does not contain any limit point other than 0 itself. So these results depend on the particular metric. So results may vary depending on the metric. If we change the metric, we will get different values for closure, interior and boundary. Thank you.